Hi, Anna, Marcin, and Anika. Oh, Anika, I'm supposed to know you, but I still don't know you on person. Hi, Ivan, Alexandra, Maja, nice to meet you all. So maybe some of you don't have cameras or is not able to open them. But I guess it's also important for you to know each other because those of you that are continuing with the other phases of the course will eventually meet and also work together in groups. So I think it's important that you start knowing everyone from the beginning. Yeah, I know Dorothea and Marta is saying they don't have cameras. I know some of you don't have cameras. So don't worry, but it's a good idea to everyone know and meet everyone. Okay, so good afternoon, everyone. I think they are all in the afternoon uh, time zone. Anika probably is still in the morning. But yeah, most of you, I don't know. So some of you maybe are in the morning or in the evening. So the objective of this class today is to introduce a little bit about concepts of modeling. So you have already you had already some classes regarding model data, on how to get model data, how to use model data. So today we are going to speak a little bit about how that model data is produced. What is that thing? A model, how does it work? The different types, different methodologies. So it's a very, very basic class about modeling. So I will not enter into the deep mathematics that exists behind models. So it is meant for you to have an idea of how it works from a global perspective. Okay, so also you are free of interrupting me whenever you want if you have any question. Okay, so don't be shy. I'm here exactly for that, for answering your questions. And also, there is no silly questions. That's a very important thing, okay? All questions are valid and don't be afraid of asking questions, yeah? Okay, so I will share my screen. Okay, my name is Flavio. I'm coming from University of Algarve. So basically, I will move to the next slide. Basically, we are discussing here today what is a model, what is that of transporting a property, why is that important in a model, and we have many ways of doing it, using an Eulerian perspective and a Lagrangian perspective, so we will see the differences between the two perspectives. Then we will talk a little bit about discretization. It's something that we need to do in order to create a model. There is discretization in space and discretization in time. And then we will talk a little bit about model limitations. We'll talk about boundary conditions and initial conditions. What is downscaling? The different types of models and the different types of numerical methods. What is an operational model? What is data assimilation? What is analysis and reanalysis? And what is model calibration and validation? Okay, so these are the basic topics that we are touching today. And starting by the first situation, what is a model? I would like you to see this picture here and tell me what you see. So, and you are free to open your mic and interact with me. What do you see here? Anyone? You can also write in the chat if you want. Okay, we have people here saying apple. Yeah, picture and fruit. Okay, so all valid answers. Yeah, apple and monkey. Oh yeah, and monkey. Yeah, yeah. Very good drawing. Okay, yeah, yeah. So yeah, in fact, I would say it's a very good drawing of an apple. Yeah. And this, what do you see here? Is another very good drawing of an apple, I guess. So some of you prefer the first one, some of you prefer this one. This one is quite different, but even though we managed to understand it's an apple, right? And this one is also a good drawing of an apple. So yeah, this one, it really looks like an apple. Some of you said it's a picture of an apple. Some of you were a little bit more acute in your observation and managed to say, although of all this bright here, that it really looks like the painting of an apple. Okay, so none of this is an apple. Okay, so those of you that answer an apple, you are wrong. It's not an apple. An apple is what you have in your home and that you manage to eat. That is the real apple. These are representations of apples. So basically they are models of apples. Okay, so they share some of the properties of the real apple, but they don't share all the properties of the apple. For example, none of these have seeds. None of these have smell. None of these have taste. Okay, so some of the properties of the real apple, of the reality, don't exist in this representation. So this is a model. Okay, and like these models, the models that we are going to talk about, the mathematical models, they are also representations of the reality, that they share some of the properties of the reality, but they don't have all the properties of the reality. Okay, so they are simplifications of the reality. And whenever you do a simplification, you get something that is a little bit distorted. It's not the reality itself. Okay, so whenever we work with models, we must be prepared for errors in the models, not our errors implementing the model. Even if we implement the model correctly, we must be prepared for the model to have errors, because it's only an approximation of the reality. Okay, so if you want to define it a little bit more exactly, you can say it is an abstracted representation of a complex real-world system. So it's an abstraction or a simplification of the reality. Okay, and why do we use model? We use modeling for basically three different activities. So, and to explain those three activities, we can use this kind of formulation, which is, it's a very generic formulation. It says that if we have data inputs that we call U, and we have an operator, which is the model, that picks these inputs and applies some methods or some operations to the inputs and transform them into outputs. Okay, so this is a modeling activity. And what we are used to, so the most logic and the direct way of using a model is you have inputs, so you have you know how to relate the inputs with the outputs. So you have M, and you get the outputs. So this is the normal way of using a model. So when we use it that way, we call it, we say we are doing simulations or maybe predictions. So the difference between a simulation and the prediction is that a simulation is a generic name. It can be used for things that already happened in time, so things in the past, or things that are going to happen in the future. Okay, so if we talk about prediction, it means we are talking about predicting the future. Okay, so we are based on the past and the present to try to predict the future. Okay, and I also have here understanding, because we can do with these models things that don't exist. You see, we can play with them and try to understand the system. For example, imagine you have a model of a certain place, and you want to evaluate, for example, the importance of the Coriolis force in this system. Okay, so in the reality, you always have Coriolis force. But in the model, you can say, okay, let me disconnect the Coriolis term, and let's see what happens. What are the results without Coriolis and with Coriolis? And let's try to see what is the importance of Coriolis here. Is it big? Is it small? And what about if I don't use the wind? Is it important, the wind or not? And the tide. So we can play with the model, you see. So we can use it in scenarios that are not realistic, but that help us to understand the system and the sensibility of the system to the different processes. So that's why I have their understanding. So this is the most basic way of using a model. But I can also using a model in a different way. If I have the inputs and the outputs, you see, and I want to know how the system works. You see, which are the best equations to describe or to relate the inputs with the outputs. Okay, so this is system identification, and I can do this with analytical equations, or with equations. Let's say it that way. But I can also do this without equations. If I'm using artificial intelligence, basically, I'm trying to find an operator that links the inputs to the outputs, you see? Even without knowing the equations, I just know the relations between the inputs and the outputs. Okay, so this is system identification. And I can also have the model operators and the results. And I want to know the inputs, you see? So the question here is, which inputs will give the outputs that I want? And that is called the inverse problem. And usually it's used in management and decision making. So basically I say, okay, my output, what I want as an output is that the concentration of this pollutant cannot be higher than this, you see? Which should be the inputs so that the output will be lower than this value. So this is a management or a decision-making question. What should I do to have my system the way I want it? Okay, so these are the three main ways of using a model. So, and as I said, a model is a simplification of reality. Okay, so I'm putting this picture here just to tease you a little bit. So these are also models. So they are simplifications of reality. So when they wake up in the morning, they are not like this, right? So our models are a little bit different. They are mathematical models. And there is a big difference between the two, which is mathematical models improve with age. Okay, so if it is an older model, it is usually better than a new model. So, and these models on the right, they are not exactly the same. So you see, when they get old, they get worse than when they were young. But our mathematical models, they usually improve with age because they pass a lot of tests and we get experience with them and they get improved. And so they become better models, okay? Okay, so any question about what I've been saying here? No? So if not, I would like to pass to another subject, which is related to the way we implement models. So, and this is the basic notion of how a property, any property, a generic property, how it varies within a fluid, within a system that is a fluid, okay? And to understand that, usually I use this analogy. It's an analogy of a person that is inside the balloon and is measuring one property of the atmosphere, of the fluid, in this case is the atmosphere. So imagine you are measuring the temperature of the atmosphere, okay? So imagine the balloon is static in some place in the atmosphere, okay? And imagine the atmosphere, the temperature in the atmosphere increases in time, okay? And it is constant in space, okay? So this horizontal line here means the temperature is equal everywhere, but everywhere it is increasing in time, you see? So my question is, how much is how do you relate the variation of the temperature in the balloon, the temperature the person measures inside the balloon, with the temperature of the environment? How do you relate them? So it's pretty obvious that they will be the same, okay? So the environment increases the temperature in time, the person in the balloon is static, the increase that the person measures is the increase of the temperature in the environment. Okay, so it is pretty obvious. But now let's think on a different experiment. So imagine the balloon is located in a place where the temperature don't change in time, so it's constant in time, but it has a spatial gradient. Okay? The temperature changes in space. So if the balloon is static, the temperature in the balloon, as I said before, is equal to the change of the temperature in time. So it's zero, it doesn't change if the balloon is static. But if the balloon has a velocity and it moves, how much is the variation of the temperature measured inside the balloon related to this? How do we compute it? Any idea? Anyone wants to say something? Either using the mic or using the chat? No? So how do you relate this with these quantities? Like this, right? So you have the spatial gradient, so the temperature changes in space, and then you have a velocity. If the velocity is higher, the person in the balloon will experience a faster change. And if the velocity is lower, the person experiences slower change. okay? And you can also see in terms of units, this is correct, because this is degrees divided by meters, and here you have meters divided by seconds, so you get degrees per second. And here you also have degrees per second, okay? So this is a change in the temperature measured by the person inside the balloon, which is not due to a change in time in the environment, but is due to a change in space in the environment and the movement of the observer. You see? Now we can do a third experiment. You have the two situations together. You have an environment that increases temperature in time, but also have a spatial gradient, and the balloon has a certain velocity. And obviously, in this case, you have two terms. You have one term that gives the part of the change the person measures in the balloon. There is one part that is due to the environmental change in time, and there is another part that is due to the gradient in space and the velocity of the balloon. You see? So you have these two terms. And these terms have these names. So it's the temporal variation and the advective variation. You see? So this is a variation due to the time variation of the environment, and this is a variation is an advective variation. It's due to the spatial gradient and the velocity. In this case, it's a balloon, but obviously this is the story of every fluid particle when the fluid moves in our environment. You see? So this is how we describe the variation of a property in a fluid with these two terms. Whenever you pick a model book, this is the first term that you see, okay? And usually you don't grab the meaning of it. It's two equations, two terms in an equation, but you don't grab the meaning. And I want you to understand these two terms, what they mean. So basically you have here two methods of looking at the fluid or analyzing the fluid. One method is like being in a balloon or being attached to a fluid particle. If you are attached to a fluid particle, you say that you are analyzing the fluid as a Lagrangian observer. You see, a Lagrangian observer is moving along with the fluid, or otherwise, you can stay fixed to the earth and analyze the fluid using these two components. In that case, you analyze the fluid as an Eulerian observer, you see? And they are exactly equivalent. Either being a Lagrangian observer, and you analyze the fluid like this, or being an Eulerian observer and analyzing the fluid like this, it's exactly the same. So it's two different ways of looking at the fluid as it moves. And some models, for some applications, it's better to use this approach, and for other applications, it's better to use this approach. Okay, that's why we talk about the two approaches. Okay, I know this is a little bit, maybe at this point you find it a little bit conceptual, too much conceptual, but this is the basis of all the models that we use. Okay, and in this case, instead of temperature, I put alpha. Alpha is a generic property. For example, if alpha is V, so the property that we are transporting is the momentum, the linear momentum. The linear momentum is mass times velocity, okay? So if alpha is the velocity, this is an equation that analyzes the variation of the velocity, okay? And the variation of the velocity in time, you know, it's acceleration, okay? So this is a momentum equation. is F equal ma. So the A is computed in a fluid. It's computed like this, you see. Okay, so basically you have this equation that you are used to see for many years in physics, the Newton law for a solid. So for a solid, it's very easy because you see a solid, when you say A, you are sure what you are talking about. It's the acceleration of the center of mass of the solid. But in a fluid, every particle have a different acceleration, you see. We cannot use a single number for the acceleration. So it means that in a fluid, the forces and the accelerations depend on the position and the time. Okay, so they are fields. Okay, they are not vectors; they are fields. Field is a continuous of vectors. In every point in the space, the vector has a different value. Okay, it's a field. But even though the concepts are the same, just that it's for a fluid and not for a solid. So basically, you get these equations. So you see, now you know to interpret these terms. This is the acceleration. It has two terms, the temporal acceleration and the advective acceleration. There are some tricks here. These J's, when you repeat a J, it means you have three terms, one for each direction. Okay? Because this is a 3D field. But don't worry about that. So basically, these equations say acceleration equals to forces per unit mass. Okay? These are all forces per unit mass. So, and these are the Navier-Stokes equations. It's basically is F equals ma, but for a fluid. It's the Navier-Stokes equation. Okay. If you want to look a little bit more in detail, these forces. This is the Coriolis force. This is the barotropic force due to the water level. This is the barotropic force due to the surface pressure, so the atmospheric pressure. This is the baroclinic force due to differences in density. And this is diffusion forces. Okay, so they are all very well known. So basically, if we manage to solve these equations, we have our problem solved. We know how to compute the velocities in every point in our fluid. The big problem is that there is no solution still known for these equations. Okay, it doesn't mean the equations don't have solution. It's just that we still don't know how to solve them analytically. Okay, so mathematicians all over the world would love to solve these equations, but still didn't manage to do it. So in fact, there is a $1 million prize for the first person that managed to solve these equations. Okay, this is given by a mathematical association in the States. But even though no one managed to solve it. So the problem remains how to proceed. And in the past, before the age of the computers, what we used to do was to just ignore some of these terms, the terms that were more complex or more difficult to evaluate or less important for the flow, we would ignore them. For example, if we ignore all the terms except the Coriolis force and the baroclinic force, do you know what equation do we get? We get the geostrophic equation. It's something that those of you that are coming from oceanography or physics probably have heard of the geostrophic equation. It's the equilibrium between the Coriolis force and the baroclinic forces. Okay, but that's only valid in very large systems that are considered stationary. So nowadays we almost don't use it anymore. Okay, so what we do nowadays is we simplify these equations into, so we pick these equations and we transform them into millions of discrete equations. So basically, they are very easy equations that we can solve. Okay, they are algebraic. Only have sums and products, and they are a system of millions or billions of equations. Okay, and we must solve simultaneously all these equations. So we need huge computer to do it. Okay, so that's how we come up with models. So to do this discretization, we need, first of all, we need to discretize the space. Okay, so the Navier-Stokes equations are continuous in space. They are field equations. They are valid for every point in XYZ. In our case, when we turn into a model, we discretize the space. We say, okay, the space is not continuous anymore. It is divided by cells, and we apply the equation in each one of these cells, but not in the middle between the cells. You see? And there are a few ways of discretizing the space. You can discretize using a geographic grid like this, function of theta and phi. You can discretize using a Cartesian grid, usually for smaller systems. And you can discretize in more sophisticated ways using a curvilinear grid or even a triangular grid. Okay? This last one, has this name here, unstructured. All the other meshes before, they are structured. And this one is unstructured. The big difference between these two families of grids is that whenever you have a structured grid, it means that every cell in the grid can be identified by indexes. So even in this complex curvilinear grid, you know this cell here has an index number, A, J, K. You can say, okay, this is cell 247 in I, 250 in J, and 24 in K. You see the three directions of space. And that's very useful, because if you know the number, the indexes of each cell, you can say which are the neighbors of this cell. So you can say what is the neighbor in the north, in the south, in the east, and in the west. And that's very useful when you are creating your model. In a triangular, or even if it's not triangular, in an unstructured grid, you don't have indexes. So you can start by numbering the triangles. This is 1, 2, 3, 4, 5. When you come up here, the triangle 255, the neighbors will be the 320 and the 435. So there is no rule for the neighbors, okay? And it gives a lot of problems when we are implementing a model, okay? So that's a big problem in unstructured grids. The good thing about unstructured grids is that, you see, you can control the size of the elements. You can create very, very small, tiny triangles connected with very large triangles. And here, no. If you create a very small rectangle here, you know that all this line will be composed by small triangles. Even if you move it a little bit, but you are not completely independent, okay? So this is good for that, but it's bad. Usually when we have flows, these models are not, they possess some problems of conservation. So nowadays we are, well, in some cases we still use them, but in other cases, when it's important to assure the conservation of the properties, we are trying not to use them, okay? Anyway, and in the vertical direction, there are also many ways of discretizing the grid. So you can have Cartesian discretization, sigma or terrain following discretization, or generic discretization, where you have different methods in different points. Yeah. Okay, so this is the discretization in space, but we also need to discretize our equations in time. Okay, and there are many ways of doing that. So if in every point of my grid I compute the new value, so this I is time. Okay, I plus 1 is the new time that I'm computing, and I is the old time that I already know. Okay? If I'm computing in every point the new value based on the old values of the neighbors, you see, I say I'm using an explicit method. And it's very easy to implement an explicit method, because when I'm doing this computation, I already know this. Okay, but this is not correct. It has some error, because I should compute this as a function of the new values of the neighbors also. So what I really should do would be to use an implicit method. In an implicit method, the new value of the property in every point is a function of the new value of the property on the neighbors. You see? But the problem is that to know this, I need this, and to know this, I need this. So everything is connected, because I also don't know the neighbors, because they are at the new time. Okay? So the method I need to use to solve this is to solve a system of equations. Okay? I cannot solve them individually as I could do in the explicit method. I need to solve all the billion points in my grid all at the same time, solving 1 billion by 1 billion equation. You see? So that's why we need the model, the computers. There is a third possibility, which is to compute the new value based on some neighbors in the new time and other neighbors in the old time. If we do that, we say we are using a semi-implicit method. Okay? And if we choose correctly which neighbors are in the new time and which neighbors are in the old time, I get very simple systems of equations that are solved very rapidly. Okay? So this ADI, it stands for alternate direction implicit, is probably the most well-known and the most used method. It is a semi-implicit method that is really efficient. Okay, so it's a little bit about what's behind the machine, okay? How we do it. I know that it's impossible to explain everything, but at least you get a flavor, you get an idea of what a model do. It picks the equations, transforms and discretizes them, and needs to solve them. So let's move a little bit further and see model limitations. As I told you, you must be prepared to have errors in the models, okay? The only thing is the error should not be too big. We should maintain the error as small as possible, okay? So, and at the same time, we need our model to run as fast as possible, okay? So for a certain mesh, for a certain number of cells, you see the model is running in time. Let me go a little bit further. So the model is running by time steps, you see? So we are in time 0, then we compute time 1, then we compute time 2, time 3, and we continue in time, okay? We compute it by time steps. Imagine that you want to simulate 1 week, okay? If this time step, if this time step is 1 second, you will have a certain number of time steps. It will be many thousands of time steps, all the seconds of 1 week. If this time step is 1 hour, you will have much less time steps. And if this time step is 1 day, you will only have 7 time steps. Okay, so it would be great to have as less time steps as possible because the model would run faster. But the thing is, if I increase, if I increase the time step, the delta t, I will decrease the execution time. But what happens is sometimes the model don't give good results. So you have here, this is a real case. This is done using a real model. This is the water level, okay, in a tide system, this time tide system. And this was done with a small delta t, so many time steps, and the result is very smooth. But if you increase the time step, trying the model to be faster, suddenly you get a crazy result, you see. Somehow here, it gets crazy results. And if you look at the map of velocities, it becomes completely wrong. You see, instead of this nice flow of tide entering the system, you get crazy values that has nothing to do with reality, okay? When this happens, this is one of the model limitations. We say the model entered into instability. It's a mathematical problem with the equations of the model. Okay? So, and this instability is controlled by this number. This is a non-dimensional number that computes a ratio between the distance one fluid particle travels in 1 delta t, you see, is the velocity times the delta t. So it's the distance a fluid particle travels in 1 delta t when compared with the size of the mesh, with the grid size. You see, so if Cura is larger than 1, it means the particle will move more than 1 cell in 1 delta t. If it is smaller than 1, it means the particle will move less than 1 cell in 1 delta t. Okay? And when the Cura is very large, you get this instability. Yes? And it depends on the model. If it is an explicit model, the Cura must be really, really small. In fact, it cannot be never higher than 1 if it is explicit. If it is implicit, if it is fully implicit, in theory, the Cura number could be as high as you want, but in practice, it also gets instability. And if it is an ADI, you have Cura numbers that can be larger than 1, but cannot be that large. Can be 10, can be 5, depending on the system, but cannot be completely independent. Okay, so this is one of the problems with models: limitation, instability, and we control it using the Cura number. Okay, another limitation. So imagine that you have an initial condition that is like this. Imagine you are measuring the concentration of a pollutant in a river, okay? And the river runs in this direction, and the initial pollutant concentration is like a triangle of concentrations, you see? And then you have a velocity in the river, and the velocity will move this concentration downstream. But imagine the river has no diffusion. We know real rivers always have diffusion. But in a model, we can, as I said, we can play with the model and say, okay, what happens if I don't put the diffusion term? So if I don't put the diffusion term, I only have the transport of the pollutant. So all this concentration will move downstream and I will get something like this. So this is the correct solution in a river without diffusion, okay? So, but if I use a model to simulate this, even if I cut the diffusion term, so if I put it as 0, the diffusion term, and don't enter with the diffusion, what I get is something like this. You see? I never manage to have the correct solution. I always have a solution that is similar to a model with diffusion, although I didn't use the diffusion term. You see? So this is an error that happens in all models, and we call it false diffusion. Okay? So this is false or numerical diffusion. It's due to numerical properties of the models. You see, I have here two solutions. One is upwind, the other one is quickest. I don't have time to explain what it means. So there are ways of trying to reduce this problem, but it's impossible to solve it completely. Okay? So this numerical diffusion, I can enter a little bit more in detail to try to explain you why does it happen. And it has to do with the discretization of the mesh. So let's imagine that you have the same river, okay? The river goes in this direction, and you have a velocity v. Instead of a triangle, my concentration now is just 1 in the first cell and 0 concentration in the rest of the river. Okay, so maximum concentration in the first cell and 0. All the rest of the river is clean from the pollutant. You see? So what happens when the model starts running, when the water starts moving? Remember, we don't have diffusion here. We just have advection. So, and imagine the Courant number is 1. So, as I said, if the Courant number is 1, in 1 delta t, the particles will move exactly 1 delta x, so the space of 1 cell. So, if t equals 0 in this situation, when t equals 1, the water will move 1 cell. Exactly. So it will move then. You see? So this is the solution for t equal 1. For t equal 2, it will move like this. For t equal 3, it will move to this position, and so on. So if I draw all the positions, this will be the position of the pollutant in every t, every instant of time. Okay? So this is what happens when the Courant is 1. Now imagine the same situation, but when the Courant is 0.5. So if the Courant is 0.5, a fluid particle will move only half of 1 cell, right? So a particle that is here, it will move only half a cell. But the problem is we don't have half cells. We only have concentrations in cell 1 and in cell 2. We don't have anything in cell 0.5. It doesn't exist. So that's why we call it discretization. So the space, it's not continuous anymore. It is composed by cells, which are discrete. They are not continuous. So the best my model can do in this situation is this. You see, it is conserving the property. So the total amount of pollutant is correct, is 1, but it has distributed the pollutant between the 2 cells. And then if I move to 2, this one will move half a cell. So this 0.5 will be divided 0.25 here, 0.25 here. And this 0.5 will move to here and will distribute 0.25 here and 0.25. The two 0.25s give 0.5 and you get this. And the same again and again. So after a few iterations, you get a concentration like this, you see? But this is physically wrong. This is due to the discretization, you see? Because the model should, in the reality, it should be a one moving slowly like this, but because the model don't have half cells, what happens is this. Okay, so this is the core of the reason why we have numerical diffusion. Yeah, and we cannot solve this. There are methods to improve, but we cannot solve this. So the thing is this a big problem? Is this a big problem in my simulations? Luckily, we don't have systems without diffusion. You see, we always have some natural diffusion. And usually the natural diffusion is smaller, is higher than the numerical diffusion. So when we calibrate a model, we are somehow compensating for the numerical diffusion. So we are using a diffusion coefficient in our model that is only enough with the numerical diffusion to give the best results. You see? So because our systems also have natural real diffusion, most of the time this is not a problem. In some cases, it may be a problem and we need to be careful about it. But in most of the cases, it's not a problem. I don't have more time to explain you the tricks when it becomes a problem. For example, in the vertical direction, in stratified systems, numerical diffusion can be a problem. And that's why we have many different grids and discretizations or coordinates, as we used to call in the vertical direction. But anyway, we managed to solve it more or less. Okay, so these problems that we solve with our models are called initial and boundary condition problems. And they are called initial and boundary condition problems because they need initial conditions and they need boundary conditions. Okay? Initial conditions are conditions in every cell of my model at time 0. Okay? And there are many ways of doing it. We can, for example, start a system from 0, saying, okay, all the properties are 0. And that's okay in a very dynamic system. Imagine that you are simulating an estuary. And the residence time of the estuary is a few days. So you know that if you simulate just a few days, even if you start with completely wrong conditions, initial conditions, after a few days, all that information was lost, was forgot by the system, and you start having good results. So you need a model spin up, so a time that you know the model is computing wrong, but they are just propagating the forcing, and after that spin up time, the model will start having good conditions. Okay? But this is just okay in very dynamic systems. If you imagine that you are simulating the entire Atlantic Ocean, okay? The residence time and the turnover time in the Atlantic will be a few centuries. So if you start with 0 everywhere, so velocity is 0, constant salinity, constant temperature, it would take you a few centuries to get good results. So it's not possible to start from 0. Okay, so in that case, you need to start from a certain condition. Usually it's climatic conditions, climatologies, and you interpolate into your cells and you start your model. Okay, there is also this data assimilation, which is a method of creating the initial conditions based on observations. Okay, I will talk a little bit more about data assimilation later. Okay, so these are for the initial conditions. And then for the boundary conditions. So the boundary conditions, they are not supplied inside the system. They are only supplied at the boundaries of the system, you see. But they are supplied in every time step. Okay? And they are supplied at the surface, they are supplied at the bottom, and they are supplied in every lateral boundary. Okay? And I just put here a few names. I won't have time to explain you more. So these boundary conditions usually always bring problems to our model solution, because basically we are replacing the part of the reality that we don't want to compute. We are replacing it by certain values at the boundary. But the reality outside the boundary is not replaceable. So some strange effects start happening at the boundary. That's why usually when I want to study something around here, I always create a very big mesh with the boundary very far away from the place I want to study, so that the problems that arise at the boundary somehow dissipate before I arrive to the place I want to study. Okay? And there are many mathematical tricks like sponge layers and flux radiation schemes and radiation condition, flux relaxation schemes and radiation conditions that I may use also to avoid problems in the boundaries. Okay? Okay, so basically we have now observations, and I'm putting here this picture of Eurogoods, where you know Eurogoods is the European system for ocean observation, where we have observations from many sources, from buoys, from gliders, from Argo buoys, tide gauges, ferry boxes, high-frequency radars, and even animal-borne instruments. Okay, so we have measurements from many different platforms. And we ingest all these informations in the model so that we create the forcing and the initial conditions to run our model, and the boundary conditions to run our models. And then we use the models to give answers to problems in the society. And this Copernicus is the European model, or the European center that retrieves data and runs the models and displays the results. Okay, and they have very large systems. They have a global model for the entire world, and they also have regional models, and you will have a lot of classes talking about Copernicus. So I won't talk more about this. The only thing is that to say that usually the resolution, the spatial time resolution in Copernicus, because it's a very large domain, it's not as precise as we would like. So sometimes what we do is downscaling. And downscaling is basically using the Copernicus solutions, or whatever solution you have, large-scale solution, and observations to create regional and local high-resolution models. Okay, so this is downscaling. You create a local model with a very high resolution that then you can use to give more answers to the society. Okay? Okay, so these are just two examples that we are running here at the University of Algarve. we have this SOMA operational model that runs in the coast of Portugal. And we have this Cartagena Bay model that is running in Colombia, okay, based on two different projects that we have. So these are downscaled operational models. What does it mean by operational models? It means that this model is doing forecasts. This model is running every day, so we have automatic methods of constructing the data to run the model and automatically run the model and display the results. Okay, and of course this is not everything automatic, so we need an operator to look at the system to see if it ran, if there was a problem, so it's supervised, if you want. Okay, but being operational means that every day the model runs and you create forecasts of the future. Okay, so a little bit about types of models. We have basically three different types of models: finite differences, finite volumes, and finite elements. Okay, in the big difference between finite differences and finite volumes is that in the finite differences, we transform the differential equations, those equations that we don't have solution, into algebraic differences equations. Okay, and in the finite volumes, we don't start with the differential equations, we start with the control volume equations already discretized in the cells, and we create the algebraic equations from these control volume equations. So the most important difference between the two is that finite differences have conservative problems, so they cannot conserve completely the variables, and the finite volumes are conservative by nature. Another big difference is that the curvilinear mesh in the finite differences must be implemented using a mathematical method called coordinate transformation. And in the finite volumes, we don't need to do coordinate transformation because all the equations are applied to cells in the real world domain. Okay? Finite differences are easy to teach, so they are still used in the university to teach. Okay? But usually they are not used anymore in models. Most of the models. Some models still use it, but most of the models don't use it. Okay? Finite elements is a completely different family of models. They transform the differential equation into form functions, families of form functions, and then the specific function that is chosen is the one that minimizes weights in the equations. Okay, they also have conservative problems. It's difficult to include the advective terms, and the good thing is that they are easy to implement in unstructured grids like triangular grids. That's why they are still used, because they are good to implement in triangular grids. But even though I don't want to say they are not used, many models are based on finite elements, but I would say the majority of the models nowadays use finite volumes. Okay. Okay, so returning to the equations, we see that for any property, we have the variation of the property, you already know this, and you have the diffusion of the property, and then you have sources and sinks. Okay, I told you that if alpha is V, so this is the Newton law, is the Navier-Stokes equation. In that case, the sources and sinks of momentum are forces. So these would be the forces that I showed you before. But if instead of V, we have a certain component, certain concentration of some property. This is the standard equation for every component of the every property. It can be concentration of ammonia, concentration of nitrate, and can also be concentration of phytoplankton and zooplankton and so on. Okay? And in that case, if we implement all these properties, we get a biogeochemical model. Okay? And the sources and sinks will be the processes that transform one property into the other. For example, nitrification that transforms ammonia into nitrate, and then nitrate into nitrate is nitrification. Okay? And grazing will transform phytoplankton into zooplankton. Okay? And mineralization will transform organic matter into the nutrients. So all these transformations are implemented here in the sources and sinks, you see? So basically, if you have a biogeochemical cycle like this, every one of these boxes are properties, concentrations of some property that are moved in the system using these equations. Okay, you have one equation for every property, and all these arrows, these connections, are the sources and the sinks. For example, as I said, grazing is the zooplankton eating the phytoplankton. So grazing is a sink of phytoplankton. If you have a lot of grazing, phytoplankton concentration decreases. But it's a source of zooplankton. Okay, so in the equation of phytoplankton, grazing will be a sink. But in the equation of zooplankton, grazing will be a source. You see? So, and if you do the same for every property, you get a biogeochemical model. You must run all the properties at the same time. Okay? Okay, and in sediment transport is the same. If alpha is the sediment concentration, the sources and sinks will be erosion and resuspension and so on. And you need to compute all the sources and sinks based on the properties of the system. Okay, so the idea is the same in every model. Okay, for water temperature is the same, alpha will be temperature, and the sources and sinks are solar radiation, sensible heat, latent heat, light attenuation, and so on. Okay, so these are the basics of different types of model. So, returning to the operational modeling cycle. As I said, the model runs every day. So in day one, it takes, imagine, 12 hours or 8 hours to run in day one. And it runs a forecast of 5 days. So in 8 hours, the model managed to simulate 5 days. So this is simulation time, not the time the model needs to simulate, okay? So next day, in day 2, the model starts running again and simulates another 5 days. And in time 3, the same. And in time 4, the same. So in every time, if you go there, you have 5 days of forecast, okay? What happens is that the model solution, if you don't ingest observations into the model solution will start to deviate from the reality. Okay, so our forecast starts being worse. So every few days, you need 2 or hours or whatever, every period, you need to reinitialize the model with initial conditions that are closer to the reality, to the observations. Okay, and we do that by using data assimilation. Okay, we assimilate observation, and we restart the model with new initial conditions that are closer to the observations. Okay? Okay, so this is the more or less the definition of an operational model. So let's talk a little bit about data simulation. So basically, what I said is you have observations and you have a model. So if we don't feed the model with new observations, the model will deviate from the reality, right? Because the model have errors, okay? But only people that never went to the sea to do observation believe the observations are perfect. So the observations are also imperfect. They also have errors, okay? So we cannot assume when we are using the observations to improve the initial condition of the model, we cannot assume the observations are correct. I mean, we must include an error in the observations, you see? So you include observations with the error of the observations, the model with the error of the model, and you use the two to create a better initial solution for my model, okay? And then you run the model for a few days or hours or weeks, whatever, it depends on the model. And then you use it and you ingest new data to get a better solution, and so on and so on and so on, okay? So this is the basics of data assimilation. So I have another graph here that explains a little bit better what I'm saying. So imagine that one point here represents the entire state of my system, okay? It means it represents all the values of all the variables in every cell, okay? So this is not a number, this X is kind of a matrix with all the values of all the points in my model, okay? So we have the values, and we should know the error of my model. Okay? And then these are the observations, and I should also know the error of the observations, okay? And my new initial condition should minimize the difference between the model and the observations, you see? So it should be something like here with an error also. So I should assume an error to the new initial condition, but it minimizes, so it's kind of midway between my model and my observations. You see? So this is the trick about the data simulation. And then we run the model one more time step, one more assimilation step. And then I do new observations and I assimilate it again, and I get a new initial condition and I run the model again. You see? So by this, I managed to have, you see this green line is trying to always stick closer to the blue line, which is kind of the truth. You see, the truth don't pass through the observations, but also don't pass through the model. It passes midway along, trying to minimize the errors of the observations and the errors of the models. Okay? Obviously, we don't know the truth. That's the problem. But we assume this is the best we can do. Okay? So I have just 10 minutes. Advance a little bit more. There are many types of data simulation. It can be sequential, intermittent, or sequential, continuous. And we also have non-sequential, intermittent, and non-sequential continuous. When it's non-sequential, you can go back in time, okay? So you get this and you get back in time. In that case, it is called analysis or reanalysis in these cases. Okay, whenever you go to commands and you see reanalysis, they are using these mathematical methods. Okay, so they have a long-term forecast, they have long-term observations. Obviously, they use the observations to the forecast to do these simulations, but then they use them again all together. You see, instead of a long time, they pick, for example, 1 month, and they use it again all together, all the observations during 1 month and all the forecasts during 1 month, and some additional observations they didn't use in real time because they were not available in real time, but at the end of the month already exist. And with all this, they smash it up all into a new reanalysis, you see, which is typically closer to the truth than the forecast. Okay, and it's there in the commands, can be used for long-term trends, for climatology, for whatever you want. Okay, so just to finish, before we use a model, this is really, really important. Before you use a model, you need to calibrate and validate the model. Okay, it's not elective. You cannot choose between calibration and validation. And calibration and validation are not synonymous. Okay? Many people do that mistake of thinking that calibration and validation it's a synonymous, and they use it indistinguished between calibration and validation. So basically, the steps to have a model that can be used is first identify the equations, create a computer code, verify the model with tests, simple tests usually, then correct the model, and then stage 4 is calibration. And calibration is to pick data, real data, okay, and compare the data with the model solution and run many different simulations with different values of the calibration parameters. Okay, so for example, in a model, a calibration parameter can be the coefficient of rugosity that reduces a certain bottom stress, or can be the coefficients that are used to compute the turbulent viscosity in the model. So those kind of coefficients, or the coefficient that is used to compute the drag coefficient from the wind. Okay, and we have certain values of those coefficients, and we move them, we change them, and we compare. So we do many scenarios, many different runs with different values of those coefficients, and we choose the set of coefficients that gives the best comparison with the data. Okay, so when it happens, I say my model is calibrated. But even though I cannot use it yet, because after being calibrated, so it may be kind of addictive to those situations that I use. So I should use the model again, now without moving the calibration coefficients and using a different situation, so a different data set, you see, and see if the comparison is also good. So basically, I'm running the model with one condition, and I calibrate it. I change the calibration parameters to get good results, and then I take my model out of the comfort zone and run it in a different situation without moving the calibration parameters to see if it also performs well. If it happens, I say the model is validated. Okay? And please don't forget, the calibration data set must be different from the validation data set to put my model out of the comfort zone. You see? Okay, and when this is ready, I can use my model. Okay? The big thing is how to compare? So whenever I say I compare the model with the data, how do I compare it? There are many ways of comparing it. You can use root mean square errors, where you compute the errors of every point of the model compared to the observation. Okay. For example, this is underfitting. Okay, so the model is not fitting the data, the observations. But this is overfitting. Okay, because we are not getting into account the errors of the observations. Obviously, the nature don't behaves as this model. The nature behaves as this model here. All the rest, these are noise. This is noise. This is due to the observation error. Okay, so overfitting is also bad. But if you use this will give probably, this one will give a better result than this. But obviously the model is wrong. Okay, so we must be careful when we use this kind of metrics to evaluate the models. Okay? Another thing that sometimes we don't see in my comparison is when we have phase differences. For example, if the blue is the observation and the red is the model, I see there is a huge error here. So it seems the model is completely wrong. And if I use root mean square error, it will give a very bad error to the model. But because I'm a human, I can see a trend here. This is just a phase difference. So if I correct the phase of my model, so the error will be much smaller. Okay, so sometimes we must use other methods to see these phase differences. For example, in processes that are like waves, we can use the decomposition into components. For example, if it is a tile, we can decompose the tile into its constituents and compare and also decompose the model into its constituents. It's what I have here. So I have the model and I decompose into the components. I have the tile signal, the observations. I decompose into the components and I compare the two and I get amplitude errors and phase errors. You see? And I can also use the power spectrum of the model and of the observations to compare the two. So there are many methods of comparing models. Okay, so I'm right on time to finish my presentation. So just a small recap what I've been showing. Basically, what is a model? We saw it is an approximate representation of reality. We saw also the transport of a property. We did that example of the balloon. So we saw the difference between Eulerian and Lagrangian, and we saw they are equivalent, but they produce different model types. Okay. Then discretization in space and time. I talk about meshes, and in time, explicit, implicit, alternate direction, implicit. Model limitations, I talk about instability, numerical diffusion, about the current number. I talk about initial and boundary conditions. We saw they are both necessary. They produce errors, and they influence the results. I talk about downscaling to get higher resolutions. Usually I use boundary conditions from general circulation models. We talk a little bit about types of models, the numerical method, the variables that are computed. We talk about the operational modeling cycle. So we saw in operational models, the model runs every day, and it restarts from an analysis using data simulation. And then we talk a little bit about data simulation, analysis and reanalysis. And we saw that data simulation combines the model with observations to produce analysis. And finally, we talk about calibration and validation. that is always necessary, and there are many ways of comparing that. Okay, so this is what I'd like to show you. We have time for questions, so if you have any question, please go ahead.